Oh yeah, we can do that later. Um, all right. So what do you have for number 1? E. Okay, I believe you. I think that is correct. Number 2.
I had something different.
C.
C. 2 is C. Number 3. Number 3 is A. Now, a few people were asking me again about this. Remember, this is y prime is cosine. So you could, especially when you have just x's here, right? We could think about like the antiderivative, right? It's y prime is cosine. So what is the y? Sine, right? So you're looking for something that looks like a sine, and you look at this, right to the origin would be. Now, of course, it could be shifted up and down, but that would be a way to get that one pretty easily when they just have x's. Same thing with number 1. You know that, forget the 0.3 a minute, when you have x squared, what's the antiderivative of an x squared? X cubed, right? It's going to have an x cubed. So when you look at E, you know, it's kind of that S shape kind of comes up and then goes like this. And so again, when you have just x's, those are probably the easiest ones. You know, we talked about plotting a few points so you can see what the slope is. But I think on the ones with x, you can almost just kind of do an antiderivative and see what it's supposed to be pretty easily. But then when you get into ones like number 2, now it's just a y, so now you're looking for horizontal rows of slopes, you know. But then you might have to plot a few points just to kind of tell for sure. Like on here, number 2, you put a 1 in for y, you get 0. I always like to look for 0 because those are nice slopes to find, right? Nice flat 0 slopes. So when I look at this, I say, hey, if I put a 1 in there, I'm going to get 0. So when y is a 1, which would be right across here, I should be getting a 0 slope, and it looks like there is there. Looks like they're flattening out. So that's how you can do that pretty quickly. And then, of course, you get 4, it's got an x and a y, so that means it's got to be, it can't be one of these that's got rows or columns. So it's got to be something like F, or it's got to be something like G, or J, or K, really are the only options, right? So you could plot some things. So what did you have for 4? G, okay. Number 5, when I look at that one, I'm thinking of an x squared, right? When I see 2x there, I'm thinking of an x squared. I'm thinking, I want to find one that's a parabola. So I think you can use that antiderivative thing a little bit. Remember, that only works, though, when x is your input variable, okay? So looking for a parabola one, you know, is pretty easy. It looks like it's got to be B, right? I got a note about you guys. Something. Bands. Orchestra. Orchestra. Isn't that just a fancy name for band? Oh, no. Wait. Okay. All right. Do you guys play Calculus the Musical? Have you ever done that? It is a thing. Is that a thing? Okay. Well, you guys missed it. Here, let's play it real quick. Which one? The limit one? That was better. Lionel Richie. Lionel Richie. Don't be saying anything bad about Lionel Richie. Oh, gosh. Well, what's going on? That one's not as good. Second edition. That's the second edition. Oh, it's about this. So X gets infinitely close to X. I thought this one was good.
I don't mind if there's no value at this point. It's fine. Find a value anyway.
This is especially for the orchestra.
If I come from the left or the right, if they
This is from Calculus the
I
Musical.
will find that a limit's alright.
Can't believe you questioned if that was really a thing.
Sometimes I see that X approaches A.
I know there's another good one.
So
Oh yeah, that was pretty good. Oh, shoot.
And minima, just take derivatinima. Happiness, now just assess the 0, 0, 0, 0. Don't forget you must inspect the endpoints as they are suspect. Find the values of our function, look for high and low. Local maxima are on an interval. Local minima are on an interval. Global maxima aren't on an interval. Global minima aren't on an interval.
See this, I'm so glad Mr. Matt's here because this is all about learning styles. I got my orchestra students coming in, I'm playing the music, right? Am I recording? Good. Put this on the internet and probably win all kinds of awards. All right, here we go. 6. All right, 6. What did we say 5 was? B. 6. D. Okay. 7. I. 8. Is like a cosine, right? That antiderivative, that'd be cosine, actually negative. 8. Not A. 8.
What did it say?
8 is A. Right. Okay, now the other worksheet. Now the other worksheet had that section where they were y equals, right? So if that would have been y equals sine, then A looks like y equals sine, right? But this is y prime is sine, so y would be the antiderivative. That's cosine. So you guys that came in late, I was saying that when you have just an x, in there, you can, of course, you know it's going to have just columns, vertical columns of slopes, but also you can plot some points. But even quicker than that, you can look at it and say, you know, I can do an antiderivative when there's just an x in there and kind of tell what the function's supposed to look like. So the antiderivative of sine would be negative cosine, and if you look at h, it does look like a negative cosine where it starts down low and then comes up, right? And so that could be a way to find it a little faster too, okay? But we were saying that if you get one that just has y's in it, what did we say 6 was? D. So when you get one that just has y's, you know you're looking for ones that have horizontal rows of slopes that are the same. So then you got to plot some points. Well, what I would do is I would usually look, I like to see 0. Slope of 0 is easy to find, I think. So here, if y's at 3, I know I'm going to get a 0. So right up here at 3, sure enough, looks like it's kind of flattening out. And also down here, now we don't have quite enough values really to see it, but I think it's coming down here and it's kind of, you can see it's kind of, it's going to level off at 0. So when y is at 0 and when y is at 3, you're going to get 0 slope. So I think that's how you can find that as well. Okay? All right, what about 9? F, okay, 10, K, 11, J. And again, on those, some of you had asked me, I think it was on the other worksheet, if you have a 0 on the bottom, what's an undefined slope look like? That looks like vertical. Unless it's 0 over 0. Now the only, and we're going to get into that today actually quite a bit with our limits. When you have 0 over 0, that's undefined, but it's like a special kind of undefined. Remember that? With limits, you kind of keep going. When you look at J and K, what's happening there is actually there's no even part of the picture there, because what you're going to have is kind of like hyperbolas. They're going to kind of come in like this, or sideways, or this way. And as you get there around 0, you're going to have no point at all. It will never cross through the origin, okay? And it'll be vertical at the x-axis when y is 0, because you'll have these sideways kind of hyperbolas, and right there will be like the vertex, if you will, of it. And that's why it'll be a vertical slope there. So on the x-axis is why we get undefined, which would be vertical slopes, okay? All right. So that's that one. And then, of course, our slope fields, and you know, 6 probably looks a lot like what we just talked about, although it was x over y, but it's probably very similar. And then you had to match these. Let's look at the matching ones. So what'd you have for 7? D. Now let's talk about that, because the difference here is this actually says y equals. Now I will not probably do this on the quiz. It's going to be differential equations where I give you y prime, but y equals 1. So remember, these are actually slope fields or graphs of y, the original function. So normally with a slope field, you're given a y prime differential equation, and the picture is the y. Okay? Well, here I actually gave you the equation is the y, and the graph is the y, so they should match. So y equals 1's got to be D, right? And it's weird because you're like, well, wait a minute, that's not y equals 1, that's y equals 1, y equals 2, y equals 3. What it is like y equals 1 plus c. You know what I mean? So it's like y equals 1 with a vertical shift. That's kind of what's happening there. All right, so y equals 1 over x squared. What'd you have there?
H. Oh wait, x squared or x?
I'm sorry, I was going the wrong way. Go to number 8. Yeah, let's do that. Y equals x is H. Y equals x squared, C, x cubed, F, 11, yeah, A. 1 over x squared, okay? 1 over x squared kind of looks like a 1 over x kind of a thing here, where it's just in this quadrant or this quadrant, or it's in this quadrant, okay? When x is 0, it would be undefined, which would be at the y-axis, right? Vertical asymptote. 12, 13, and 14. Now let's talk about why there's absolute value around that. You can't put a negative into natural log. So normally on G here, a natural log would come up and then go like this, but there would be nothing over here because you can't put a negative into natural log. So to get the other half of it, we'd have to make any negative inputs positive. So you put absolute value around it, and then you can get negative x's, because then the bars would turn it to positive. If there were no bars here, then there would be no slopes over on this side. Okay, so that's why there's the absolute value there. We'll talk about that more when we get into antiderivatives later. Okay, so these are ones more like what you would get. So 15 is B, because it looks like it'd be an x squared, so it should be a parabola. 16 should look like an e to the x, right? Y prime equals y. That's one we've talked a lot about. 17 is C, and 18 A. And right, and that looks somewhat. That'd be a lot like the one you graphed on that front page, right? Or no, it was y over x. Or was it x over y? It was y over x. Okay. All right. Now, the other part of this was the bottom part was to actually sketch the solution curve. So I told you you'll probably do that. I'll probably ask you some matching on the quiz, and then also give you some initial conditions, have you sketch those. So 0, 2, so you come in here, that'd be up here, and so it would just go up, and then 0, negative 1, so now you follow those slopes, and that would go down like so. Okay? And then this one, if you go through 0, 1, which would be here, that seems to be going like this. Now the problem is you don't have a whole lot to go on here. It does look like it flattens through here, so it's got to kind of flatten, and then what you have is an asymptote, so it goes up like that. The ones that I give you, will have more little slope segments on them, so it'll be easier to do. Negative 3, 0 would be way over here, and so that looks like it kind of goes up like that, and then just kind of goes down like so, and that's what it does actually. Okay, so they look kind of different there depending on which initial condition you have. All right, so those are the things you need to be able to do. We did not, on today's homework was Newton's law of cooling, so when it comes to the quiz, we got to be able to do Newton's law of cooling, like number 23 and number 24 in the homework, which pretty much covered what you need to know for Newton's law of cooling. You need to be able to match your slope fields. You need to be able to sketch or draw a slope field and sketch the solution curve in a slope field, right? So the things we went over on Thursday and Friday, those are the 4 things you have to be able to do for the quiz. The calculator part, this will be, you'll get to use your calculator for this, so all that solving part. maybe even where you have to draw a slope field so that just in case you need to type in and calculate the slopes, or just so I can, sometimes I put things on the calculator. Remember, just because it's a calculator part, like on the AP test, just because it's a calculator part doesn't mean you'll use your calculator, right? So sometimes I'll put things on the calculator part where I know the calculator really is of no use or no help. I'll just put them on there to kind of balance out the two parts, okay? And then, of course, the things where I know the calculator would be helpful and I don't want you to do those, like derivatives or limits or something like that, those go on the no calculator part for sure. But some problems, it doesn't really matter. You wouldn't use your calculator no matter what. Sometimes I'll put those on the calculator part just to balance them out a little bit. So that's like drawing the slope field. You know, you're not going to have to go into your calculator, put it in differential equation mode, and be able to put in a differential equation so you can draw a slope field. You don't have to do that on your calculator. Matter of fact, it's probably not that helpful. If you do it and try to do that to draw your slope field, like on the front page of this worksheet, I don't think it would have been much use. It would have shown you the general picture, but I don't think it's a whole lot of use. But if you want to, you can. You know, I'm not saying you can't, but what I will do when I grade those slope fields is I will look when you draw those little lines. I'll especially be looking for the ones where it's horizontal, because I know what those are supposed to be, and the ones where it's not a very much of a slope, I want to see that they're not very steep, and the ones that are steeper, you know, I mean, just that kind of thing. Not real exacting, but they obviously have to be going the right direction and that kind of thing. Okay, and then sketching the solution curve, I want that to be pretty accurate. I want you to do a decent job with that, given, you know, within the limitations of how many little slope segments you have there. Okay, all right. So that's pretty much that with differential equations and slope fields. All right? Okay, let's get your notes out and talk about the next piece of this that we have to do today, which is the limits. And this, I think this tends to be probably the harder part of the quiz. For whatever reason, limits, I think, is just one of those concepts that, you know, once you grasp onto it, it's not bad, but it does take a little while. So there's some things you probably have to kind of memorize or, you know, remember, do this, do that, whatever. But really, it's more about the overall concept. If you understand that, that helps a lot, because I see people do some strange things, and it's because you're trying to kind of memorize, you know, what do I do here, what do I do there? So you really want to try to put that together.
The test is on
Thursday, yeah. Okay? All right, so let's review here first what we've done so far with limits. Okay, we had those videos about the cars meeting, and we're going to rewatch a little bit of that, and then we've got some new ones to watch. But the diner burning down and all that stuff, okay? So what we've done so far is we've done limits, and let's talk first about graphs, because I think that's the easiest, right? If you have graphs, that's pretty easy to do limits, okay? Now, we're not going to probably have many questions with graphs on this part, okay? It's going to be more about the equation, okay? Because there's not much more to say when it comes to graphs, on limits. But I think to help understand the concept of what's going on, it's good to think of them graphically. So where does the limit not exist on this picture? At x equals -1. That's it.
Maybe -4.
And then you'd have that issue with the endpoints, but we're not going to get into that, right? I won't ask any questions about the endpoints, okay? So at -1 is the only time the limit does not exist, because that's when the cars would not meet, okay? Now, cars meeting and not meeting is a good thing to think of to help you with the concept, but it's not formally correct, right? We want to say the limit on the left, kind of like the song, if you were paying attention to the song, right? They're talking about from the left and the right. The limit from the left of -1 is 2. And the limit from the right of -1 is 1. The limit from the left does not equal the limit from the right, so therefore the limit at -1 does not exist. Okay? But again, it's the cars don't meet. We don't care that there's a hole or not a hole there. We don't care if there's a value there on the graph. Okay, that doesn't matter. Now, and Jared said something important. He said approaching. Limits are all about approaching, not what actually happens at that point, not exactly at -1 or what the y value is at that point. It's what it's approaching. So that's a key word to keep in mind with limits. You can see over there today, it says solve. It was funny. I was writing that stuff up there this morning, and I thought, what are the chances Mr. Manson's going to walk in the week of Christmas? He's going to put him. I thought, I'll put him up here. Not that I only put those up there because Mr. Manson. All right. So anyway, and so that's the new part today is what do we do with infinity? Okay, infinity. So most of our emphasis today is going to be things with infinity. Not every problem will have infinity in it, but infinity is not a number. Infinity is not a number, so you can only approach infinity. So like you guys were asked yesterday on the calculators, right? It was given, or last week, something about the calculator given infinity, right? Again, infinity is an idea. Infinity is a concept. Infinity is something you approach. Infinity is not a number. Sometimes we treat it as a number, and it can be thought of in some instances like a number, but other instances it doesn't behave like a number. So we got to be really careful. Like, what's 2 times infinity?
To infinity and beyond.
It's infinity. What's infinity? This is like the big anniversary of Toy Story or something. There was just a thing, a show on TV about like 20 years.
Last year. It was last Thursday.
Like 20 years or something. Yeah, it was on TV because it's been like 20 years. Okay. Anyway, good. Or. Oh, when it came out? Yeah. When Toy Story came out? 204. BC. Oh, the good old days. Good old days.
Back when I was a boy.
Yeah, I was gonna say. Yeah,
Pixar has nothing.
I'm getting old, but geez, thanks, man. All right. So anyway, so especially when you're talking about infinity, it's really important to talk about it's approaching infinity, right? Now, we'll sometimes say plug in infinity, but I mean, that's really informal language because you plug in numbers, right? So we'll talk about plugging in infinity, but what we're really saying when we do that is that whatever we're plugging into is getting bigger and bigger and bigger. So it's important to understand that concept. Okay, so at 1, the limit is what? At 1, the limit, -2. Again, it's what? It's the answer to a limit is a number. So let's get back to this idea of what we're finding. The answer to a limit is a number, and the number is what the y values are approaching. So we don't care that there's this diner burned down and moved to a new spot. We don't care. It's the y values as you come from the left and the right. The y values are getting closer and closer. They're approaching 2. That is the limit. Even though they never get there or there's not a point there or whatever, they are approaching 2. So that is the limit. Okay? Now, oftentimes, the limit is the y value. So that's nice. Like at 2. What about at x equals 2? What's the limit? 0. The y value, and remember what they said in that video, the intended height of the function? It's what the graph intends to reach. So many times that just is the y value. In a nice normal graph, that's what it is. Okay? It is the y value. So that's why we do substitution first in a limit problem. As x approaches 2, we plug in a 2. Because a lot of times that just gives us the answer. Now, how do you know you're not going to get tricked? How do you know when you plug in a 2 and you get out a 4, how do you know it's not this situation? Well, do we know of any functions that would do something like this? What kind of a function would make a graph like this? A piecewise. You're not going to get tricked into that situation. You plug in a 2 and it gives you a 4 and that not be the limit because it'll be obvious. It's going to be a piecewise. It's going to be some kind of weird function. All the basic e to the x and sines and exponentials and all those kind of functions don't do that. So when we plug into one of those, we're not going to get tricked in that way. So when we plug in and get out a number, that's our limit, okay, most of the time. And if it's not, it will be some sort of function where we'll be able to say, hey, something weird's going on. Okay? What's the limit at 3? 1. Again, we don't care that there's a hole. Now, if there was an equation, we tried to plug in a 3, we'd get undefined, we'd probably get 0 over 0, remember? And that's where we said keep going. You get 0 over 0, this is probably what's happening. So you do some other stuff to find out what is that value, where is that hole. So when we have graphs, it's pretty easy to do the limits. I think the concept is fairly simple to do. So we'll always think back to that, because what we're going to be focused on are equations. And what we want to do is when these weird things happen, when we plug in, get 0 over 0 or 6 over 0, what we want to be able to do is picture what is the graph doing when these weird things happen when we plug in. Okay? What is the graph doing? Because if we knew what the graph was doing, then that would help us, okay, to figure this out. All right, so those are the things we were doing before with limits. All right, so here's just a rewrite of the things we did before. So if you want to put this in your calculator or not, that's fine. Although, some of the problems that we do on this quiz will come from ones like before. Right? It's going to be a mixture. We're just adding to the pool of types of limit problems we need to do. Okay? Now, remember last time we were doing limit problems, I had them type in your calculator, draw a table, look at the table. We're not going to do that. Okay? We're not going to have any of those. This is all going to be just the no calculator. We're not going to get into a lot of messy algebra, though. Remember when you had to do common denominators and conjugates and stuff? There won't be a big emphasis on that at all on this, okay? It'll be more about, well, you'll see what it'll be about as we get into this. Okay, so what can happen if you do a limit as x approaches some number, as x approaches 1, x approaches 2, x approaches 3? Well, a couple things can happen. You can plug in and get a number out. Then that's the answer. The limit exists. That's your answer. And again, we're not going to be tricked when we have some function because, you know, and there'd be something else, because that would have to be like a piecewise or something like that. So we would see that coming. Number 2, we get 0 over 0. If we get 0 over 0, we keep going. Maybe we factor. That's where we did least common denominator, conjugate, whatever. So the limit might exist. We just keep going and see if we can get a number out. Then the other thing that can happen is we get something like 6 over 0 or 7 over 0 or negative 3 over 0. And that might happen after we had 0 over 0. We keep going and then we get that. Well, what is that? That is the limit does not exist. Now, that's where we stopped last time. If you ever got 7 over 0 or negative 3 over 0, we just stopped. We said does not exist. Well, we're going to go a little farther with that now. Why does that not exist? Well, I think I mentioned this before. But when you get a number over 0, here is what is happening. You're getting some sort of infinity situation. You're getting some sort of vertical asymptote situation. Okay? So, obviously, in a vertical asymptote situation, the cars aren't going to meet. It's just going to go up and up forever. Right? So the limit does not exist. But what we will do is we'll take it one step farther. So on the quiz Thursday, if you get a does not exist, you're going to have to take it a step farther and say why. Now, I think maybe on that quiz we said the limit on the left, limit on the right. Because right now, think back to the graph a minute ago. Why didn't it exist? Because the cars didn't meet. Well, the limit on the left was different than the limit on the right. So what about one like this? Well, the limit on the left is infinity. That's what we'll say, which technically is not good because infinity is not a number, right? The limit's supposed to be a number. But what it is it tells us, it's still telling us it does not exist, but it's telling us a little more about what's happening. On the left, it's going to infinity. On the right, it's going to negative infinity. So your answer still does not exist, but then you're giving some more information about what's happening on the left and the right. Okay? So we're going to be getting into that today, so we're going to be dealing with infinity. All right, let's look at a few examples here. Okay? So we got 2 scenarios with limits that involve infinity. Okay? So we'll take a look at this first one here. limit as x approaches 3 of this function right here. So again, this is all going to be no calculator. Okay? So the first thing we do is what? Plug in a 3. So what do we get when we plug in a 3? Right? Get 11 over 0. So we go back to this previous page, and we're down there on choice 3. Right? So as soon as we get 11 over 0, right away we are going to say, does not exist. But we're not going to stop there. Okay? We're not going to stop there. What we're going to do is we're going to check the limit on the left, and we're going to check the limit on the right. Now remember, this is all going to be no calculator. Okay? Now we could graph this function and get a look at what it is. Okay? But the idea is here we don't really need to. So what is the limit as x approaches 3 from the left? How could we know what the y values are?
Plug in a 2.
We could plug in a 2. Okay? So 2 would be 4 plus 5 is 9. 2 minus 3 is negative 1. So what's that? Negative 9. Not very helpful. Say it again. We're going to have to get closer than that, right? So what would be closer than that to the left of 3? 2.99999 would be good. Now you say, well, that's hard to plug in without a calculator. Actually, it's not. Because let's think about that. 2.99999 is almost 3. When you take 2.99999 times 2, what do you get? Almost 6. Right? I mean, think about it. We're talking about a little smaller than 3. You take that times 2, you're going to get a little smaller than 6. Little smaller than 6 plus 5 is little smaller than 11. Now, as it turns out, that part's not really going to matter. Now, I could do that. I could just little smaller than 11. Okay, 10.999, whatever. Now, I can actually write an 11 there. That part's not going to matter. It's the bottom that's going to matter. Okay? But I'll go ahead and write that. What when I put 2.99999 minus 3? Okay? Negative 0.0000, as many zeros as you want, 1. Now, a lot of times what I will end up writing on a problem like that is I will just write 11, and I will write really small negative. Now, I don't care if you write that or write that, whatever. Maybe it makes more sense. Maybe we should write this. Maybe this would make more sense, to be honest with you. Sometimes people are confused by this, so maybe it's better to just write this, actually. So what is...
German shorthand is the term for small.
Yeah, what is basically 11 divided by a negative 1 millionth?
Infinity. Negative infinity.
Negative, really big number, right? I mean, think about it. When you divide by a really small decimal, you create a really big number, right? And the vice versa. If you divide by a really big number, you create a really small number. You divide by a billion, divide by a trillion, you create a really small number. So that's how we're going to think about infinity. Okay, so what's happening is you get really close to 3 from the left. The bottom becomes a really, really small negative. So you're dividing by a small negative. So this left side of 3 is going to go to negative infinity. And we're going to circle that. What about 3 from the right? That'd be like 3.00001 times 2. That'd be a little bigger than 6. Plus 5 is a little bigger than 11. So that'd be 11.00001. But again, you see what I mean? That doesn't really matter. We can just call it 11. But then this is going to be 3.00001 minus 3. Right? And so that's going to be a positive, really big number. So what we've just found out by doing that is that this graph, we don't know what it does anywhere else. But we know that when x approaches 3, right? Now we knew we had a vertical asymptote as soon as we got 11 over 0. I mean, because that's what you have when you get a number other than 0 divided by 0. That's representing a vertical asymptote. On the left, but what we found out is on the left of 3, it's going down here, and on the right of 3, it's going up here. Now, it's possible they both could have went the same. It's possible they both could have went to negative infinity, or they both could have been going to positive infinity. But we still say does not exist, because they never meet. The cars would still never meet. But clearly they don't meet when one's going this way and one's going that way. Now, it's not, you would not have to write this picture here. But I just wanted to put it into the graphical terms. That's why the limit does not exist, because the cars will meet. But here's how we can see what's happening. Okay, so we're going to want to take that extra step. Now, type that in your calculators. Go ahead and get your calculators out. I didn't get the hats because I didn't plan on this, but this isn't a bad idea. But just go over next to the 9 and the same place you find your derivatives. My guess is it says undefined. Now, I wish it would say does not exist, but because technically that's the language we want to use is does not exist. No, just do 3. X approaches 3. Yeah, just do the original problem. Say undefined. Undefined. Now, do this for me. Go up and grab it and hit enter and paste it down again. Take the bottom and square the bottom. Take the bottom and just square the whole bottom. Now it says infinity. Now, so let's talk about that. So if you square the bottom, so when you put 2.99999 in here, minus 3, it's negative, it's a really small negative. What happens when you square a really small negative? A really small, even smaller actually, because right, if you take 1/4 and square it, you get 1/16, right? It actually gets smaller. So you take a really small negative and square it, it becomes an even smaller positive. So this one where we got negative infinity would become, so they both would have been positive infinity. So what we'd have had is a graph where they were both going up towards infinity. So the limit still does not exist. But notice the calculator gives you that little extra piece of information. It says infinity. What that means is both sides are going to infinity. So it says the answer is infinity. Technically, the answer is still does not exist. Because remember, a limit either exists or it doesn't exist. If it exists, that means it's approaching a number. And infinity is not a number. So when we say infinity is the answer, what we're really saying is it does not exist, but both sides are approaching infinity. Okay? But since both sides were different infinities, it said undefined for the other. Okay. Now, this might be a good time to watch one of these videos.
Between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, in this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Now remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3, because when we plugged 3 into f, we got a constant divided by 0.
Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit
very
as x
similar to the one we
approaches 3
just
from the
did.
left of f of x is negative infinity.
Okay.
Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal. In this section, we'll delve into the mysterious and ancient relationship.
Okay, so that's one example of how infinity gets involved in limits. It's actually something we have already seen, right? We already ran into this, but what we've added now is this part where we actually could plug in numbers really close to the left, to 3 on the left and right, and actually plug them into the function and see what we get. So that last piece there is new. In chapter 2, we just stopped and said it does not exist, okay? But now, the second way that infinity gets involved is as x approaches infinity. Now that's a whole new ballgame because we haven't done that before, okay? So let's talk about this. First of all, you cannot go from the left and the right of infinity, right? So this is a whole different question. Even though it looks like a limit problem, it's a whole different question. Because now what that is saying is as x approaches infinity means as x gets what? Bigger and bigger and bigger and continues to keep getting bigger and bigger. So it's a whole different question than as x approaches 3. All right? So we treat it a lot differently. Now, sometimes we say we could do substitution. We could just plug in an infinity. I mean, we could do that. Okay? So we could say here, all right, plug in an infinity. What's 2 times infinity? Infinity. Plus 5. Infinity. The top is essentially infinity. What's the bottom? You have infinity minus 3. Still infinity. Now, yeah, so you would think 1, but remember, 0 divided by 0 was not 1. It was keep going. Well, infinity over infinity is the same thing. It's not 1. It might be 1, but it might be something else, and it might be does not exist. Right? So we don't know. This is also indeterminate. Now, tomorrow we're going to talk about a rule that involves derivatives. That's why it's in this chapter, that you can use on a 0 over 0 and infinity over infinity. But right now, we're not going to use that. We're just going to think our way through it. So what we're saying is the top's getting really big and the bottom's getting really big. Okay? So what do we do? Well, there's, again, the thing we'll learn tomorrow is one way we could do it. But another way we could do it is we actually ask this question. We say, okay, as x gets really, really big, how much difference does that plus 5 make? If I've got $1 billion in my pocket, and I see a 5 laying on the street, I'm Warren Buffett. Well, if you're Warren Buffett, you're going to pick it up. That's how he has so much money, right? He's a cheapskate. I'm a cheapskate, but I don't have a lot of money. But if I've got $1 billion in my pocket, do I even pick up that $5 bill? Yeah. You're right. I know it's a 5. Okay, bad example. I got $1 trillion in my pocket. You pick it up?
Yes.
What if the wind's blowing and it blows away? I got $1 trillion in my pocket, and I reach in to get my keys, and a 5 drops out, and the wind blows it across the parking lot.
Then you better go chase it.
You're ruining my great example.
I wouldn't do it.
I would not even go do it. I got $1 trillion, and that 5's blowing across the street.
You have somewhere in the money.
That's right. I'll get my driver. Go get it. That's right. Go, my servant. I'll have him go get it. Point is, as x gets bigger and to be honest, and we're going to talk about this more tomorrow, but to be honest, $1 billion or $1 trillion really is not that big, right? In the grand scheme of things, $1 billion, $1 trillion is really not that big. So when we talk about x going to infinity, we'll talk about million, $1 billion, $1 trillion, but actually those are not that big. So as x gets bigger and bigger and bigger, how much significance does that 5 play? Less and less and less. to where it becomes just a speck, even, you know, something you couldn't even see as x gets really big. So what that means, as far as how you work this is essentially just 2x on top. As x gets bigger and bigger and bigger, the plus 5 becomes so insignificant as to just ignore it. And the bottom, what happens on the bottom?
It just becomes X.
It just becomes x. So now, remember, x is getting bigger and bigger and bigger, so that means the x on top is growing at the same rate as the x on the bottom. We could just cancel those, and the answer to this one is actually 2. So what, well, but think about it. Think about it, because what's going to happen as x gets really big, and you guys got your calculator, so let's put them in. So as x gets really big, so let's say x is a 5. That's not very big. Let's say x is a 5. 2 times 5 is 10. 10 plus 5 is 15. I'll write this down. And then let's put a 10 in here. 10 minus 3 is 7. So what's 15 divided by 7?
2.7.
2 point something. But now let's let x be 1,000. So now we would get 2,005 divided by, and what's 1,000 minus 3? 997. Take 2,005 divided by 997. You get 2.011. You see what I mean? And as we and that was just x being 1,000. So if x was 1,000,000, we get 2,000,005. That's none of zeros. So 2,000,005 divided by 1,999,995. 7. Thank you. Now my guess is that's 2.0000 something, right? So does that make sense? So as x gets bigger and bigger and bigger, this is going to be getting closer and closer to 2, right? Because the top and the bottom, the 5 and that minus 3 are becoming pretty insignificant. And I didn't do that right there. It's not 1 either, right? It's 1,000,000 minus 3, 999,997. Okay, so I typed that. Okay, so basically it's getting, the 5 and the minus 3 are becoming so insignificant that it's basically 2,000,000 over 1,000,000, which is 2. Okay, so now what about negative infinity? Well, x is getting smaller, but I would say getting big negative. So we're talking about a negative 1,000,000. Well, so what would you have? You'd have essentially a negative 2,000,000 over negative 1,000,000. What is that?
2.
It's not negative 2, it's still 2. Because what you have is a negative on the bottom and negative on the top. Still going to cancel to be 2. So it's going to turn out that it doesn't matter if it's going to positive or negative infinity. Okay? Now again, same thing. I would say to myself, if I was working this problem, I'd say, okay, x is getting really big, but it's negative. So this would be a really big negative plus a 5. Well, the plus 5 is insignificant, so that's 2x. Here I'm going to have a really big negative and take away 3, so it's still a really big negative, but the 3 is insignificant, so it's x. The 2 x's cancel, and we just get 2. Both x's are negative, but they'll cancel, and we get 2. So there's your limit. Now, so that's what we're going to do. I mean, on these kind of problems, we're going to say what's happening to that function as x gets bigger and bigger and bigger. Okay, that's the question, so you'll think your way through it. Now, let's talk about that graphically. What does that mean graphically? As x gets really big, where's that at on the graph? Way out to the right. Now what that is saying is that x is that your outputs are going to get closer and closer to 2. What are we talking about there? That is a horizontal asymptote. Now, I think I told you this earlier in the year. It's okay for a graph to cross a horizontal asymptote. It can't cross a vertical asymptote because that's where the function is undefined. You can cross a horizontal asymptote. Because all a horizontal asymptote says is what's happening way out there. And so what's happening is this is getting closer and closer to 2. Now, it's a little bigger than 2. Remember we were getting 2.000 something? So actually what's happening is it's leveling off from above. What about here? Well, this would be like, no, I don't think so. I think it's actually above also. Because it would be, oh yeah, you're right. So this would be like negative, this would be like negative 1,000,003, and this would be like 2,000,005, right? No, this would be, because it'd be negative 2,000,000 plus 5, so it'd be negative 1,999,995, right? So this would actually be about 1.999 something, so it would actually be below. And so what happens is you're getting this. Now remember what they said, what we said before, there's a vertical asymptote on this one. We already talked about this, right? This graph at 3, and we said it was coming down here like that, and it was going up like that. So it kind of finishes the graph for us. We knew there was a vertical asymptote because of the work we did up above. And down here, now we're seeing what happens way out to the right. So limits as x goes to infinity is all about horizontal asymptotes. Okay? But it's what is happening to this function as x gets really, really big. All right, let's see. Oh, videos. So let's look at the rest of that video. So we got to go through this.
In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote.
See, you can see the horizontal asymptote parts of this
Take a
problem.
look at the graph of f at x equals 3. Remember, an asymptote is a line which a function
Theirs
cannot
is
reach.
plus 1, ours is
Here we
plus
have an
5, but we
asymptote
said
at
that
x
was
equals 3,
insignificant, right?
because
So
when we
whether
put
it's
3
plus
into
1 or
f,
plus 5,
we got
notice the horizontal
a
asymptote's the same.
constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity.
Okay.
Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger, f gets closer to 2.
That's kind of what we were doing when we plugged those values.
Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height.
Okay.
When I was explaining the last example, I said that x was getting infinitely large, and we translated that mathematically as the
He's
limit
going to work
as
this
x
a little
approaches
differently with
infinity.
some algebra, and
Now,
I
this
want
type
you
of
to kind
limit
of
is
see
called a
it.
limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. Now, that's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to
Notice it says
calculate.
if it exists.
All you have to do is
So instead of
compare the
talking
degree
really don't
in the
exist.
numerator and denominator of the given function. By the way, the degree is the highest exponent. So, if we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, if we don't write a power, it's inferred to be 1. Now, in this case, the degrees of both the top and bottom of the fraction are equal, and therefore the limit at infinity of this fraction is going to simply be the coefficient attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1, and we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. What happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist, because it's infinity.
Okay, now he just went through that really fast. And that's, you can memorize that way, but again, I want you to understand the concept. So what he was saying there is he said, if the degrees are the same, now this only works for polynomials. What if you have sine, or what if you have e to the x, right? And then we have to think about it. So this only works for these simple algebraic polynomial kinds of functions. But what he's saying is if the degree is the same, you just take the coefficients on that highest powered term, and that's your limit. Well, why? Because we said the plus 1 or the plus 5 didn't matter, right? And the minus 3 didn't matter. So I really want you to understand that concept, that's why you can just look at the highest powers. I call it high powers dominate. When x gets really, really big, lower powers of x get so much smaller than the highest power that they become insignificant. Eventually, they become insignificant when x gets really, really, really big. So that's why you only have to worry about the high powers. And then, of course, if it's x to the fifth and x to the fifth, they'll cancel, right? That's why if the powers are equal, you can just look at the coefficients, because the powers will cancel, and there you go. Okay, well, now let's talk about this last thing he says. If the numerator degree is higher, if you have an x squared over an x, and the lower powers won't matter, what's x squared over x? X. That reduces to x. Now, what happens to x as x goes to infinity? It goes to infinity, right? Or if you have x to the fifth over x to the third, what does that reduce to? X squared. What happens to that as x gets really big? It gets really, really big. So the answer would be infinity. Actually, the answer would be does not exist, and then you could say infinity, right? So that's what he says here. If the numerator degree is higher, then the answer is infinity. Technically, it does not exist, and then infinity, right? What if it's the other way around? What's x to the third over x to the fifth? 1 over x squared. What happens to 1 over x squared if x is getting really big? The bottom's getting really big. You got 1 divided by a really big number, which is a really small number. It's getting smaller and smaller going towards 0. That's why you get 0, which is still a horizontal asymptote, right? But it would be at 0. Okay, and I think I've got some examples there, but I wanted to talk about that because he kind of goes through that really fast there, and he might show a few examples.
In conclusion,
Oh, no, I guess
if
they're
the
right.
limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote at x equals c. Whereas, if the limit as x approaches infinity of f of x equals d, then f has a horizontal asymptote at y equals d. One word of caution. When we say that a limit equals infinity, we're actually saying that that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.
And I want you to say that. I want you to say does not exist. Okay? I mean, geez, that's a scary looking small problem. So, yeah, don't do that. So, does not exist, and then say infinity. But there at the end, right before he got to that part, I can't pause it, but he gave the two different ways that limits can involve infinity. We can have vertical asymptotes, like the first example. X approaches 3. You plug it in, you get 11 over 0. That's a vertical asymptote. That means your outputs are going to infinity. Then the other side of that is if the inputs are going to infinity. If x is approaching infinity, what do you have? Well, that's when you have horizontal asymptotes. So those asymptotes go hand in hand with limits and infinity. Okay, so to wrap this up then with some examples, then I want to get into some where they don't just have powers like that, because those are the simplest kind. And so I want to get into a few that don't, and then we'll move on. Okay, so this kind of summarizes that, what we were just saying. Okay, so you have something like this. Okay? Yeah. limit as x goes to infinity. So, and the same would be true for negative infinity on these as well. Okay? The same would be true on negative infinity, right? You might have to think about it just a little bit as far as plugging in negative numbers. Okay? So we would have to think about that a little bit as we get into it. But so this, as x gets really, really big, what matters here? The only the x cubes. Now, here's the thing. A billion squared is a really big number. But it's not nearly as big as a billion cubed. And a billion isn't even that big. You get out to a trillion, or what's a 1 with 100 zeros after it?
Google.
A Google. Not the search engine, but G-O-O-G-O-L. Google. G-O-O-G-O-L is a 1 with 100 zeros. Now, a trillion is a 1 with 9 zeros. Right? No, that's a billion. A billion is a 1 with 9 zeros. A trillion is a 1 with 12 zeros. A Google is a 1 with 100 zeros. And what's a 1 with a Google of zeros? A Googleplex. That is unfathomable how big that is. Okay? Matter of fact, you know what? We got it. Get your calculators out. Just so you understand how much difference it makes to just add a few zeros, just a few zeros to a number. So take $1 million. Let's say you had $1 million. We're going to talk more about infinity tomorrow, but we just got to talk about this. Say you had $1 million and you were going to spend $1 every second. How long would it last? So the question is really, how long is 1,000,000 seconds, right? You have $1 million, a lot of money. You're going to spend $1 every second. So what would you do? Divide this by 60. That'd be minutes, right? What do you get? Give me a decimal.
16,766.
Okay? So that's minutes, right? And then divide that by 60 again, and now we get hours. And then divide that by, we're not even going to sleep. I mean, we're going on a spending binge here. 24. So that would be days. So $1 million would be gone in 11.57 days. But now, we're going to take $1 billion. Well, you're probably sharp enough to know what's going to happen if you go back and repeat all that. The final number is just going to be 3 decimal places bigger. What was this, 11.57? So it's going to be 11.57 what? 4 point something. That's days. Look at that. Just from 1 million to 1 billion went from 11.5 days to 11,000 days. Divide that by 365. How much?
31.7.
So now, for $1 million, you would spend it in 11.5 days. But if you had $1 billion, and let's face it, here's somebody's a millionaire or billionaire, does it really make a difference? I mean, they're just really rich, right? Well, the millionaire will be out of money in 11.5 days. The billionaire will be out of money in 31 years. And what if you're a trillionaire? 31,000 years to get rid of $1 trillion. Right? I mean, I think that puts it in perspective a little bit. How much just going from 3 or 6 zeros to 12 zeros, what a difference that makes in the size of the number. So imagine going from 12 zeros to 100 zeros. How much bigger that would be. And then a Google, I mean, it's just, you can't even fathom how long that would be. Okay? So when we talk about numbers getting bigger and bigger and bigger, you got to kind of keep that in perspective. That 1 million, billion, trillion really are not even that big. But even those, you get to $1 trillion, and it's just almost too much to imagine. 31,000 years to spend $1 trillion, compared to 11.5 days to spend $1 million. Now, anyway, back to this. So the point if I take 1,000,000 and square it, yeah, that's a big number. But it's nowhere near as big as 1,000,000 cubed. And when you get out to really big numbers, and you compare a cubed number to a squared number, the squared number is insignificant. So the only number that really matters here is this and this. The x cubes cancel, and so that's why they were saying we just take, when the powers are equal on the top and the bottom, we just take the coefficients and we get 1/2. Okay? Now what about this one? The only one that really matters on top is that, and on the bottom is that, right? Now that reduces to what? Now what happens as that, now remember you're doing x goes to infinity. And don't forget to add on a does not exist. Now what if that said x approached negative infinity?
It'd still be
No, it'd be negative infinity. So if this was approaching negative infinity, it'd be negative really big number over 4, positive 4, so it'd be negative infinity. Does not exist, be negative infinity.
So the limit actually doesn't exist.
Limit actually does exist, and what that would be is a horizontal asymptote at 1/2. That's what you would have happen. Okay, a horizontal asymptote. When you get an actual number here, that's your horizontal asymptote as x gets really, really big. Right? What about this one? When the power on top, the only one that matters is 2x squared. On the bottom, the only one that matters is 3x cubed. That would be 2 over 3x, right? So as x gets really big, the bottom's getting really big. 2 divided by a really big number is approaching 2 over 1,000,000,000. It'd be 0.0000002, right? It's getting smaller and smaller. It's going towards 0, which is an actual answer. That's not a does not exist. That's a horizontal asymptote at the x-axis, right? It's approaching 0. Okay, so those are the situations. Now, don't forget that, and this is the part that sometimes people forget about, is this is only when it's x approaches infinity. If I took any one of these problems and change it to x approaches 1, then it's just plug in a 1, right? Then it's just plug in a 1. Don't do high powers dominate. High powers don't dominate when you approach 1, right? High powers only dominate when x gets really, really, really big. So it's only in x approaches infinity kinds of problems. When it's x approaches 1, you just plug in a 1, right? So understand, there are two different types of situations. Okay, so now let's look at a couple of others. So let's look at this situation here. Here's where we can't think about just the powers. Okay? We have to actually think about what the function does, which I like that. I like those kind of problems. You have to think about what's happening. So, x is approaching infinity. So, we ask ourselves, what happens to this as x gets really, really big? That is going to get really, really big, right? Getting really, really big. What about e to the negative x? Isn't that going to basically turn into 0? I mean, it's 1 over e to the x. Now, no, you can't flip it down here. No, no, no. You do not flip that down to here because that's got this minus sign on it, okay? But it's 1 over e to the x. Now, what happens to the bottom there as x gets really big? What happens down here? Gets really big. But if you take 1 divided by a really big number, it goes down to 0. Okay, 1 divided by a really big number is 0. I think we were talking about that. That was what we were talking about on the calculator. I think if you type in 1 divided by infinity, because there is an infinity symbol on your calculator, I think it'll say 0. Right? It'll say 0. Now, if you say 1 divided by 0, I think it said undefined, I think. But if you do 1 divided by infinity, it'll say 0. What it's really saying is a limit. It's saying 1 divided by a really big number is getting closer to 0. Okay? All right. So what's infinity minus 0? That's a really big number. Right? So in other words, this part doesn't matter. So it's kind of like that high powers dominant. As x gets really big, this is getting really big, and this is just getting so small as to not even matter. So this essentially becomes e to the 3x over 4e to the 3x. Well, what is that? It's just 1/4, because the e to the 3x's would cancel. So it's kind of the same thing. It's very much the same thing. We're looking at part of that as x gets really big, the e to the negative x just becomes nothing, and it's essentially insignificant. So we get this, which reduces to that. So this would be 1/4. Okay, let's do this one. As x gets really big here, what happens to sine outputs as x gets bigger and bigger?
Spinning and
It's just going to bounce between -1 and 1, right? Imagine the x graph, or the sine graph, way out here. It's just going to bounce between -1 and 1. What's the bottom going to, so a lot of times I'll just write that here. I'll just write on top, that's going to go from -1 to 1. What's the bottom going to be as x gets really big? It's going to get really, really big. So what happens if you have a number, some decimal between -1 and 1, divided by a really big number that's getting bigger and bigger and bigger? It's going to get closer and closer to 0. Now, it's going to alternate between negative and positive, right? So what's happening there, and this is that thing with crossing, what's going to happen is you're going to get this situation, where it's going to be getting smaller and smaller and smaller, but it's approaching 0. So you have a horizontal asymptote. That's what I said. It's okay to cross a horizontal asymptote. This is an example. Okay? Because the top is alternating from negative to positive, but the bottom's getting bigger and bigger. So your number you get when you divide is smaller and smaller and smaller. And it's just going to be getting closer and closer to 0. If you flipped it,
yeah, you did x squared plus 1/sin.
now you got a problem. That's really weird. Well, because here's what happened. You'd have this really big number, and you'd be divided by a positive and negative, and it'd be getting bigger. So you'd be up here, and then you'd be down here. And then what happens when sine is 0? No,
Or, oh, no, they wouldn't.
it'd be undefined, right? Because sine could be 0, right? So every time at pi, at 2 pi, at 3 pi, at 4 pi, every time sine is 0, you'd be getting undefined. So it'd be going up and then down and then up and then down. It'd be like vertical asymptotes all over the place, probably. Almost like a tangent graph, probably. And it would be up here, and it'd be down here, and it'd be up here, and it'd be down here, and then it'd be undefined in all those places. So that'd be really weird. So I probably would never even ask you that. Okay, but you think your way through those kind of problems. All right. Now, I don't even remember why I drew these. I'm not even sure why I drew these on here. I just wanted to point out, like, this is a 0 over 0. This is what happens when you get a 0 over 0. I think I wanted to remind you that. When you get 0 over 0, you got a hole. So that's where you keep going. And you probably will get an answer. Like in this case, it'd be 1/2. I think maybe that happens on the next problem. Maybe that's why I have it on here. And here you'd have -1 would probably be like a 6 over 0 or something, right? And that's how you know you'd have a vertical asymptote. And then that's how then you check the left and the right. So this is kind of summarizing what we did back here, right? You get 11 over 0, you check the left and the right, see what's happening there. So that's vertical asymptote situation. Okay, so just comparing. So 0 over 0 is a hole. You got this, and then, of course, you got your horizontal asymptotes, which is as x approaches infinity. Okay, so let's take a look at what that looks like right here. Okay, so let's jot down these two problems. So the first step on one of these, plug in the number, right? This is not an infinity scenario, right? This is not high powers dominate, right? We're not talking about as x gets really big here. We're saying as x approaches 2. So we plug in a 2. And what do we get? 0 over 0. So that tells us keep going. So x minus 2 over this. Cancel. do you get? And we're done. Now, why I didn't make my graph match this problem, but what we just had there, so this is what our homework, this is what the quiz is going to look like, these kind of problems, but I want to compare it back to graphs. So what we just had was that hole right there. What we just found was the hole. In my picture, it approaches 1/2. What we just found is it would be approaching 1/4. Okay, so that's what we just found in that problem. So we're done. Okay, let's go down and do this very similar looking problem, except x is approaching -2. What do you get? -4/0. What does that tell you right away? Vertical asymptote does not exist, but we go farther. We check out x approaches -2 from the left, and x approaches 2 from the right. Now what we have is this situation over here with a vertical asymptote. They might be going opposite tails like this, or they could be going the same, we don't know. But we're just going to try. So what's to the left of -2? Well, -2.00001, right? And to the right, -2. And to the right of -2, 1.99999. That's what I'm going to think of, right? Because I need to go farther than does not exist. I got to check out the left and the right. So -2.001. So let's check it out. So -2.01 minus 2. That's like -4.00001. I really don't care about that, but it's the bottom I care about. -2.00001 squared. Little bit over 4, right? And positive 4. 0.00001 minus 4. So a positive 0.00001. What is -4.001 divided by 0.00001? -infinity. Right? Because this is getting really small down here, and so it's going to be just -4 billion, -4 trillion, right? Negative infinity. Okay, what about this? -1.999 minus 2. It'd be like -3.999 again. I really don't care. I could just call that -4 essentially. -1.9999 squared. It's almost 4, but not quite, right? Everybody with that? Actually, you can ignore the negative if you're squaring it. So it's like a little less than 2 squared is going to be a little less than 4. It's like 3.99999 minus 4. So that's -0.00001, whatever. Negative that divided by a really small negative. Positive infinity. Now listen, you know, whenever you're doing this, anytime you're doing this 0.0001 thing, you're going to get infinity. The only question here is if you're getting negative or positive infinity. We already know. When we had -4/0 or 11/0 or 6/0, we know we got a vertical asymptote. So we know we got tails. We know it, right? The only question is on the left and the right, is it going to positive or is it going to negative, right? So don't get too hung up with how do I divide by the 0.01 and all that, right? You know it's going to be something divided by a really small number. It's just a matter of which is going to be a really big number. The only question is it a really big negative or a really big positive? That's really all that matters. Okay? You know this is going to be infinity, negative infinity situation. There's never going to be one of these where we're going to plug these numbers in and get like 2 and 4 here or something, right? It's always just going to be infinity. All right. So that's a pretty good example of the types of problems we're talking about. X goes to infinity. Here, when it's just these powers, it's high powers dominate. So when the powers are equal, it's just the coefficients. When the high power's on top, the top's just going to get big. So that's that. If the high power's on the bottom's going to get big, which means it's 0. And then you get some of these with these other functions. You just have to think your way through it. Just have to think your way through it. All right. And then, of course, graphically, and then we come back to these, which is actually what we started the day with, or these kinds of problems. All right. Couple last things. I don't know that you need to write this down. We're probably going to start with this tomorrow. But since we talked about that thing with infinity here, a couple of things. Your book has a nice table where it says, it talks about uses of infinity, how sometimes we use infinity like it's a number, and sometimes that's okay, sometimes it's not. Like infinity minus infinity. Well, what did we say infinity divided by infinity was? Say, no. What did we say infinity over infinity is?
Keep going.
We don't know. That's kind of a trick question. We don't know. Might be 1, might be 2, might be 0, might be does not exist. We don't know. Kind of like 0 over 0. That's why we call it indeterminate. We can't determine. Infinity over infinity, or infinity minus infinity is the same way. Because it depends. There are different sizes of infinity. Right? In other words, an x squared is bigger than an x. Think about that. X squared minus x. As x gets really big, x squared minus x is heading towards what? As x gets really big, what is x squared minus x heading towards? Infinity. Because the x squared is getting so much bigger than the x that when you subtract them, isn't that difference getting bigger and bigger and bigger? See what I mean? Well, that's an infinity minus an infinity. Because they're both getting bigger. Just that this one's getting bigger faster. Oh, so you mean the rate? The rate of change has some determining factor there. Rate of change. That sounds familiar. Okay. So, I give you something to look forward to tomorrow. You'll toss and turn all night. You won't be able to sleep. Now, so just a couple other examples then. 1 over infinity, we just said. 1 over infinity is 0. What that really means is as the bottom gets big, the fraction is getting small, approaching 0. 3 times infinity, infinity. And again, don't write this down. We'll start with this tomorrow. 0 times infinity. See, I thought you would have learned your lesson by now. 0 times infinity. No, we don't know. We don't know. Here's what 0 times, put in your calculator. Put 0 times infinity in your calculator. Is it undefined? That's not true. The calculator screwed that up. 0 times infinity is not undefined. It didn't know how to handle it. Did it give a warning or anything? It said undefined. Here's what 0 times infinity means. It means a really small number times a really big number. Well, what happens? Well, normally if you take a number times a really big number, it gets bigger. If you take a number times a really small number, it gets smaller. Well, if you take a number that's getting smaller times a number that's getting bigger, it's like a tug of war.
The answer should be 0 though, because that's the. Oh no,
Because you're telling me that 0 times infinity can equal something like 2.
Exactly. 0 times infinity can equal something like 2 because what we're really not saying 0 times infinity, because remember, infinity is not a number. So the usual rules of multiplication don't apply. You know, the rule that says 0 times anything is 0, the anything has to be a number. Infinity is not a number. So here's what 0 times infinity really means. It means something getting small. I love this stuff. Something getting small times something getting big. It's like a tug of war. The thing getting big wants to make the product bigger. The thing getting small wants to make the product smaller. It's a tug of war. Which one wins? The rate. The one that's getting there faster is going to win. So if the one getting big is getting big faster than the one getting small is getting small, then it's getting bigger.
Okay, but wait.
It gets pretty interesting. And then I'll tell you the story about Infinity Hotel tomorrow. Okay?
I plugged in
The Infinity Hotel, yes.
negative infinity times infinity. Shouldn't that technically be undefined?
No, that should be negative infinity.
Yeah, but why?
That's a negative billion times a billion.
Yeah.
Negative billion times You're not adding them, right? You're
Well, I'm
timing.
just trying to think because like the whole.
So while you're doing your homework, think about this. If you already will toss and turn thinking about the rate of change thing, think about this. You have Infinity Hotel. It has an infinite number of rooms.
Oh, I've seen that.
Have you heard it? So don't tell. If you've heard it, don't tell.
Infinity Hotel.
And don't Google it.
What was the question about Infinity?
I've never Googled it, to be honest with you, so I don't even know what it is.
It's basically
I probably will now.
this is a mix between that and like an actual hotel chain.
Infinity.
Infinity Hotel.
Yeah, this is a problem that my college professor I had gave us. So you got Infinity Hotel, infinite number of rooms,
Yeah.
and it's full.
Okay.
And somebody comes and wants a room. Can they accommodate that person? Can they give that person a room? Well, tomorrow you will explain to me why. But it's full. There's a person in every room.
There's an infinite amount of people.
There's no empty room. So where are they going to put that extra person?
It doesn't matter because it.
That is the question for tomorrow.
So like, let's say you have like.
Oh, by the way, did you see the homework? Okay, I think it's on the assignment sheet. It's on the assignment sheet like this, but that's the homework for tomorrow.
Let's say you
So it happens when you take the infinite root.
What happens if what?
You take the infinite root of infinity. As much like the cubic root.
It could be anything. The infinite root? The infinite root. I think that is. I don't think that's a thing.
Instead of writing it all
Right. I don't think that is. That's kind of the same thing, right? The root's trying to make it smaller, and that's it. It would be like doing a number, like 2 to the 1 over infinity, right? It'd be like that. You would think that'd be getting towards 1, but the key is that's 2. But this is going to 0, right? The root. So this would be going towards 0, which is pulling this towards 1. I think you got it right. I think you got it. Well, you can do that. Here, let me grab it. So, if we had. Curious. So do infinity raised to 1 over infinity.
Dr. Zero makes sense.
to the 1 over.
1 over infinity, because that'd be a root, right?
1.
Yeah. What's the 1?
I define replaced by 1.
Yeah, infinity to the 0 or 0 raised.
I define to the 0.
So what it's saying is it may or it may not be right, but I would think that would be correct. Okay, Jasmine, you're going to do the gateway. Okay, I'll go grab that for you here.
Let me just be modest.
Macy and I did those things, so we're just wow. Bonus, but we put an A on it.